Is it possible to be in two different places at once? In the quantum realm, this isn't just possible, it's a normal state of being. So what other mind-bending secrets does this invisible world hold? Tonight, we will not try to solve every mystery. Instead, we will simply drift through this strange and beautiful landscape, exploring its truths one by one. Let these facts be like soft, glowing lanterns guiding you gently into the quiet of the night. Fact 1. Energy is not a smooth, flowing river, but a gentle, stepping cascade. In our everyday world, we experience things as continuous. A car smoothly accelerates, a light smoothly dims. But at the smallest of scales, the universe is pixelated. The German physicist Max Planck discovered that energy is not continuous, but comes in discrete, indivisible packets called quanta. Imagine not a smooth ramp, but a staircase. You can stand on one step or the next, but never in between. Energy behaves in this way, existing in specific, quantized levels. It is the first fundamental rule of this hidden world, a quiet whisper that tells us reality is built from countless tiny, perfect steps. Fact 2. Everything in the quantum world leads a double life. A single particle, like an electron or a photon of light, has a secret identity. It is both a solid, localized particle, a tiny, definite speck, and a spread-out, ethereal wave of possibility. This is called wave-particle duality. Think of a drop of mist that can, in an instant, condense into a single, perfect bead of water. Before you look at it, it is a cloud of potential, a ripple of probability. The moment you observe it, it chooses a location and becomes a solid thing. This gentle, shifting nature is the very essence of quantum matter, forever dancing between being a something and being a somewhere. Fact 3. A particle can be in many places at once. Before we measure a quantum particle, it exists in a state of pure potential called superposition. This means it is not in one single place or state, but in all of its possible places and states simultaneously. Imagine a spinning coin, shimmering in the air. While it spins, it is both heads and tails at the same time. Only when it lands, when it is measured, does it choose one definite state. A quantum particle is like this spinning coin, existing in a ghostly blend of all its potential realities until the moment of observation forces it to land, to choose one single existence from an infinity of possibilities. Fact 4. The universe is shy. It changes when you look at it. In our world, we can observe something without changing it. We can look at a tree, and the tree remains a tree. But in the quantum realm, the very act of observation is a creative and disruptive event. This is the observer effect. To measure a particle in superposition, you must interact with it, perhaps by bouncing a photon of light off it. But that single touch is enough to collapse its wave of possibilities, forcing it to choose a single state. It is as if you are trying to observe a delicate puff of smoke. The moment your finger touches it to see what it is, it vanishes, leaving a single speck of dust in its place. The universe, at its smallest scale, does not like to be watched. Fact 5. There is a smallest possible distance in the universe. Just as energy comes in tiny steps, so does space itself. The smallest meaningful unit of length is known as the Planck length, a distance so infinitesimally small it is almost beyond comprehension. It is about a trillionth of the width of a single atom. Below this scale, our concepts of space and distance simply break down. You can think of it as the ultimate pixel of reality. If our universe is a grand cosmic image, the Planck length is the single, indivisible dot from which the entire picture is made. It is the final, fundamental grain of sand on the shores of existence. Fact 6. Particles can walk through walls. In the quantum world, barriers are not always absolute. A particle can perform a magic trick called quantum tunneling. Because a particle's location is a wave of probability, there is a tiny, but non-zero, chance that some of that wave can exist on the other side of a solid barrier. This means the particle has a small probability of simply appearing on the opposite side without ever breaking through the wall. It's as if you threw a soft ball at a glass window 1,000,000 times, and once, just once, it didn't shatter the glass or bounce off, but simply materialized on the other side. This ghostly leap is happening constantly at the quantum level and is essential for processes like the fusion that powers our sun. Fact 7. Some particles are connected by an invisible thread. When two particles are created in a certain way, they can become quantumly entangled. This means their fates are linked, no matter how far apart they are separated. Albert Einstein famously called this spooky action at a distance. Imagine you have two magical coins. If you give one to a friend and they travel to the other side of the universe, the moment you flip your coin and it lands on heads, you know instantly that their coin has landed on tails, and vice versa. Entangled particles behave this way. Measuring the state of one instantly influences the state of the other, faster than the speed of light. It is a silent, instantaneous connection that defies our everyday understanding of space and separation. Fact 8. You can never know everything about a particle. The quantum world is governed by a fundamental limit to our knowledge, known as the Heisenberg uncertainty principle. It states that you cannot simultaneously know with perfect accuracy both the exact position and the exact momentum of a particle. The more precisely you measure its location, the less you know about where it is going. And the more precisely you measure its momentum, the less you know about where it is. It's a cosmic trade-off, a gentle law of the universe that insists on a little bit of mystery, ensuring that the heart of reality can never be perfectly pinned down. Fact 9. Empty space is not empty at all. At the impossibly small scale of the quantum world, the vacuum of space is a roiling, chaotic sea of energy. This is often called quantum foam. In this realm, tiny fluctuations cause pairs of virtual particles to spontaneously pop into existence, live for an infinitesimal moment, and then annihilate each other, returning their borrowed energy to the void. This constant, silent fizzing of creation and destruction is happening everywhere, all the time, suggesting that true nothingness does not exist. The most perfect vacuum is, in fact, a place of endless, fleeting activity. Fact 10. Every particle has an opposite. For every particle of matter, there is a corresponding particle of antimatter. An electron has its anti-electron, called a positron. A proton has its antiproton. These antiparticles have the same mass as their counterparts but the opposite electric charge. When a particle and its antiparticle meet, they annihilate each other in a flash of pure energy. In the very first moments of the universe, there should have been equal amounts of matter and antimatter. Yet today, our universe is made almost entirely of matter. This profound imbalance is one of the greatest unsolved mysteries in all of physics. Fact 11. Particles have a property that is like spinning, but not. Quantum particles possess an intrinsic property called spin, but it is not a physical rotation in the way a planet spins on its axis. It is a fundamental, quantized amount of angular momentum, as if each particle was born with a tiny, unchangeable arrow pointing in a specific direction. This spin can only have certain values, either whole numbers or half numbers, and it dictates how particles interact with each other and with magnetic fields. It is a purely quantum mechanical property, a hidden orientation that defines a particle's very character. Fact 12. The world is built on assigned seating. Two fundamental types of particles, known as fermions, which include electrons, protons, and neutrons, cannot exist in the same quantum state in the same place at the same time. This is the Pauli exclusion principle. It's like a cosmic theater where every fermion has its own assigned seat, and no two can sit in the same one. This simple rule is the reason that atoms have structure, why electron shells form, and why matter is stable and takes up space. Without this quiet insistence on personal space, all the atoms in the universe would collapse into a uniform, undifferentiated soup. Fact 13. The entire universe is made of fields. We tend to think of particles as the fundamental building blocks of reality, but quantum field theory tells a deeper story. The truly fundamental things are not particles, but vast, invisible fields that permeate all of space and time. There is an electron field, a photon field, a quark field, and so on. What we perceive as a particle is simply a localized vibration, a tiny, excited ripple in its corresponding field. So, you are not made of particles. You are a complex and beautiful collection of interacting vibrations in a dozen different quantum fields, a symphony of ripples in the fabric of existence. Fact 14. Light itself is a quantum phenomenon. The light that warms your face and allows you to see the world is made of countless tiny packets of energy, the quanta of the electromagnetic field. These packets are called photons. Each photon is a single, indivisible unit of light, a particle with no mass that always travels at the ultimate cosmic speed limit. Whether it is the gentle glow of a candle or the brilliant light of a star, all light is a stream of these quantum messengers, each one a tiny, shimmering piece of the universe's oldest conversation. Fact 15. There is a recipe book for the universe. Physicists have developed a remarkably successful theory that describes all the known fundamental particles and the forces that govern them. It is called the Standard Model of Particle Physics. It is the closest thing we have to a complete list of ingredients for reality. It describes 12 fundamental matter particles, 6 quarks and 6 leptons, and 4 fundamental forces carried by their own specific particles, like the photon for electromagnetism. While it doesn't yet include gravity, the Standard Model is one of the most rigorously tested and successful theories in the history of science, a testament to our ability to map the deep structure of the quantum world. Fact 16. Protons and neutrons are not fundamental. The particles that make up the nucleus of every atom, the protons and neutrons, are themselves composite objects. They are each made of 3 even smaller, more fundamental particles called quarks. There are 6 different types, or flavors, of quarks with whimsical names like up, down, strange, and charm. A proton is made of 2 up quarks and 1 down quark, while a neutron is made of 1 up quark and 2 down quarks. These quarks are bound together so tightly that they can never be found in isolation, a phenomenon known as confinement. They are the ultimate prisoners of the subatomic world. Fact 17. The strongest force in nature acts like glue. The force that binds quarks together inside protons and neutrons is fittingly called the strong nuclear force. It is the most powerful of the 4 fundamental forces, over 100 times stronger than electromagnetism. This force is carried by particles called gluons, which act as a kind of perfect cosmic glue. The strong force has a strange property. It actually gets stronger with distance. If you try to pull 2 quarks apart, the force between them increases, like stretching a rubber band. This is why quarks are permanently confined, and it is this same residual force that holds the protons and neutrons together to form the stable nucleus of an atom. Fact 18. Some processes in the universe prefer a certain direction. For a long time, physicists believed that the laws of nature were perfectly symmetrical, that if you watched a video of any physical interaction in a mirror, it would still look like a valid physical event. This is called parity conservation. However, in the 1950s, it was discovered that the weak nuclear force, which governs certain types of radioactive decay, violates this symmetry. In the realm of the weak force, the universe has a preferred handedness, a subtle but profound asymmetry woven into the laws of nature, proving that the cosmos is not as perfectly balanced as we once imagined. Fact 19. Quantum mechanics powers the sun. The sun generates its immense energy through nuclear fusion, a process where hydrogen nuclei are forced together to create helium. However, the temperature at the sun's core, while incredibly hot, is not actually hot enough to overcome the immense electrical repulsion between 2 positively charged protons. The reason fusion happens at all is due to quantum tunneling. The proton's wave-like nature gives them a small probability of simply tunneling through the repulsive energy barrier instead of having to climb over it. This ghostly quantum leap allows fusion to occur, making the sun shine and life on Earth possible. Fact 20. The future can affect the past. In a mind-bending experiment known as the delayed choice quantum eraser, it has been shown that the choice to measure a particle's property can retroactively determine the path it took. In the famous double-slit experiment, a particle acts like a wave and goes through both slits at once if you don't watch which path it takes. If you do watch, it acts like a particle and goes through only one. The delayed choice experiment shows that even if you wait to make the decision to watch until after the particle has already passed the slits, your future choice will still determine which behavior it exhibited in the past. This doesn't mean we can change the past, but it deeply challenges our linear understanding of cause and effect, suggesting time at the quantum level is a far stranger and more interconnected tapestry than we can imagine. Fact 21. The quantum world is constantly trying to become our world. A quantum system remains in a delicate state of superposition only as long as it is perfectly isolated. The moment it interacts with its surrounding environment, a stray photon, a single atom, it loses its quantum nature in a process called decoherence. The information about its multiple possibilities leaks out into the environment, and the particle is forced to settle into a single, definite classical state. This process is incredibly fast and efficient, and it's the reason we never see quantum effects on a large scale. A cat is simply too big and interacts with its environment too much to ever be in a superposition of alive and dead. Decoherence is the gentle but constant bridge between the strange quantum world and the familiar classical reality we experience every day. Fact 22. Even at absolute zero, things still move. In classical physics, absolute zero, minus 273.15 degrees Celsius, is the temperature at which all motion ceases. But in the quantum world, this is not the case. Due to the uncertainty principle, a particle can never have a perfectly defined position and zero momentum at the same time. This means that even in a perfect vacuum at the coldest possible temperature, there must still be a tiny, residual amount of vibrational energy. This is called zero-point energy. It is the fundamental, unshakable hum of the universe, an energy that exists in empty space itself, a quiet reminder that even in perfect stillness, the quantum world is never truly at rest. Fact 23. An invisible field gives everything substance. For decades, physicists wondered why some fundamental particles have mass while others, like photons, have none. The answer came in the form of the Higgs field, an invisible energy field that permeates the entire universe. As particles travel through this field, they interact with it. The more a particle interacts with the Higgs field, the more it is dragged or resisted, and it is this interaction that we perceive as mass. Particles that don't interact with it at all, like photons, have no mass and can travel at the speed of light. The Higgs boson, discovered in 2012, is the particle associated with this field, the physical evidence of the invisible cosmic molasses that gives substance to the universe. Fact 24. The most famous quantum experiment is a thought experiment. The story of Schrödinger's cat is one of the most famous concepts in quantum physics, yet it never actually happened. It was a thought experiment devised by Erwin Schrödinger to illustrate the absurdity of applying quantum superposition to the macroscopic world. He imagined a cat in a sealed box with a radioactive atom that had a 50% chance of decaying and releasing a poison. Until the box is opened, the atom is in a superposition of decayed and not decayed, which, according to quantum logic, means the cat is in a superposition of being simultaneously alive and dead. Schrödinger did not believe this was possible. He used the example to highlight the puzzle of where the quantum world ends and the classical world begins. Fact 25. Quantum physics makes modern technology possible. While its concepts seem abstract and distant, quantum mechanics is the bedrock of our modern world. The transistor, which is the foundation of all computers, smartphones, and electronics, works because of our understanding of how electrons move through semiconductor materials, a purely quantum effect. Lasers, MRI machines, GPS satellites, and even nuclear power all rely on principles derived from quantum theory. Every time you use your phone or computer, you are benefiting from a century of scientific exploration into the strange and beautiful rules of the subatomic world. Fact 26. Some liquids can flow without friction. When certain elements, like helium, are cooled to temperatures just a few degrees above absolute zero, they enter a bizarre quantum state of matter called a superfluid. In this state, the atoms lose their individual identities and begin to act as a single, coherent quantum entity. A superfluid has zero viscosity, meaning it can flow without any friction or loss of energy. It can spontaneously climb up and over the walls of its container, flow through microscopic cracks that would stop any normal liquid, and if you were to set it swirling in a cup, it would continue to spin forever. It is matter behaving in a way that seems to defy all common sense. Fact 27. Some materials can conduct electricity perfectly. Similar to superfluidity, when certain materials are cooled to very low temperatures, they can enter a quantum state called superconductivity. In this state, they have exactly zero electrical resistance. An electrical current started in a superconducting loop would flow indefinitely without any power source needed to sustain it. Superconductors can also perfectly repel magnetic fields, allowing them to levitate heavy magnets with seemingly magical ease. This quantum phenomenon is already used in MRI machines and particle accelerators and holds the promise for future technologies like ultra-efficient power grids and levitating trains. Fact 28. An electron does not move smoothly, it jumps. When an electron in an atom gains or loses energy, it does not spiral gracefully from one orbit to another. Instead, it performs an instantaneous and discontinuous quantum leap. It simply vanishes from one energy level and reappears in another, without ever existing in the space in between. It's as if a person on a ladder could disappear from the third rung and instantly materialize on the fifth, without ever traversing the fourth. These silent, abrupt transitions are the only way that atoms can absorb and emit light, and they are a fundamental feature of the quantum world's pixelated nature. Fact 29. There may be a universe where you made a different choice. The many worlds interpretation is a mind-bending but elegant solution to the measurement problem. It proposes that when a quantum system in superposition is measured, the universe itself splits into multiple branches. In each branch, one of the possible outcomes becomes reality. This means that for every quantum choice, a new, parallel universe is created. There is a universe where the cat in Schrödinger's box lived, and another, equally real, where it died. If this is true, then we are all living on just one branch of an infinitely branching tree of realities, a silent, unseen library of every possible history. Fact 30. A watched particle will not change. This is the quantum Zeno effect, named after the ancient Greek philosopher. It's the quantum equivalent of the old saying, "A watched pot never boils." If you have an unstable quantum system that is about to decay or change its state, you can effectively freeze it in place by observing it continuously. Each measurement resets the particle's evolutionary clock, collapsing its wave function back to its initial state over and over again, preventing it from ever making the transition. It's as if the universe's shy creations are too timid to change while under a constant, watchful gaze. Fact 31. Life itself might use quantum tricks. The strange rules of quantum mechanics are not just confined to physics labs. They may be at work inside living organisms. This is the field of quantum biology. For example, the incredible efficiency of photosynthesis, the process by which plants turn sunlight into energy, may rely on quantum coherence to find the best possible pathway for energy to travel. The ability of some birds to navigate using the Earth's magnetic field might be explained by a delicate quantum entanglement within their eyes. These discoveries suggest that nature, in its quiet wisdom, may have mastered quantum mechanics long before we ever did. Fact 32. The ultimate computer would be a quantum computer. A classical computer stores information in bits, which can be either a 0 or a 1. A quantum computer, however, uses qubits. Thanks to superposition, a qubit can be a 0, a 1, or both at the same time. This ability to exist in multiple states at once would allow a quantum computer to perform a vast number of calculations simultaneously. By linking qubits together through entanglement, their processing power would grow exponentially, making them capable of solving certain problems, like factoring huge numbers or simulating complex molecules, that are practically impossible for even the most powerful classical supercomputers. Fact 33. The opposite of a bit is a qubit. The qubit, or quantum bit, is the fundamental unit of information in a quantum computer. While a classical bit is like a light switch that is either on or off, a qubit is more like a dimmer switch, or even more accurately, a point on the surface of a sphere. It can be a 0, the North Pole, a 1, the South Pole, or an infinite number of superposition states in between any point on the equator. This ability to hold a rich blend of information is what gives quantum computers their extraordinary potential, transforming a simple binary choice into a world of infinite possibility. Fact 34. It is possible to teleport information, but not people. Quantum teleportation is a real phenomenon, but it is not the stuff of science fiction. It does not transport matter from one place to another. Instead, it uses the spooky connection of entanglement to transmit the exact quantum state of one particle to another, distant particle. In the process, the original particle state is destroyed. It's like having a magical fax machine. You put a letter in, and an exact replica is created at a distant location, but the original letter is shredded in the process. This technology is a cornerstone of future quantum communication networks, promising perfectly secure information transfer. Fact 35. Two plates in a vacuum will be pushed together by nothing. Imagine two perfectly smooth, uncharged metal plates placed incredibly close to each other in a perfect vacuum. Classically, nothing should happen. But quantum mechanics predicts they will be gently pushed together by a mysterious force. This is the Casimir effect. It arises because the quantum foam of virtual particles exists everywhere. However, the tiny space between the plates can only accommodate virtual particles of certain wavelengths, while the space outside can host all wavelengths. This creates an imbalance, a slight pressure from the virtual particles outside that is greater than the pressure from inside, pushing the plates together with a force born from the very emptiness of space. Fact 36. Physicists have a clever way to ignore infinity. When physicists first tried to calculate quantum interactions, their equations kept producing nonsensical answers involving infinity. The solution was a clever mathematical toolkit called renormalization. It is a systematic way of hiding our ignorance by sweeping the infinities under the rug. It works by recognizing that the values we measure in experiments, like an electron's mass and charge, already include all the complex quantum foam interactions. By setting the calculated value to match the measured value, the infinities cancel out, leaving behind incredibly precise and finite predictions. It is a pragmatic and powerful technique that allows quantum field theory to work, even if we don't fully understand the infinite chaos that lies beneath. Fact 37. Particle physics can be drawn as simple pictures. The interactions between subatomic particles can be described by incredibly complex mathematics. But in the 1940s, physicist Richard Feynman developed a beautifully simple visual language to represent them. These are now called Feynman diagrams. In these diagrams, straight lines represent matter particles like electrons, and wavy or curly lines represent force-carrying particles like photons or gluons. Each point where lines meet, a vertex, represents an interaction. These simple, intuitive drawings are not just illustrations. They are a rigorous shorthand for the complicated equations, allowing physicists to visualize and calculate quantum processes with a clarity that was previously unimaginable. Fact 38. There is a fifth state of matter near absolute zero. Besides solid, liquid, gas, and plasma, there exists a bizarre fifth state of matter called a Bose-Einstein condensate. It occurs when a group of particles called bosons are cooled to a temperature just a fraction of a degree above absolute zero. At this point, the particles lose so much energy that their individual quantum waves overlap and they begin to behave as a single, massive superatom. They lose their individual identities and merge into a single coherent quantum state. It is the ultimate quantum conformity, a cloud of millions of atoms acting in perfect, silent unison. Fact 39. Time has a preferred direction because of the weak force. Why does time flow forward and not backward? While many factors contribute to the arrow of time, one of the most fundamental asymmetries is found in the weak nuclear force. Most physical laws are time reversal symmetric, meaning they would look the same if you played a video of them in reverse. The weak force, however, is not. Certain particle decays governed by the weak force look different when run backward in time. This subtle but fundamental violation of time symmetry at the quantum level may be one of the deepest reasons why the universe has a past, a present, and a future, and why we can remember one but not the other. Fact 40. The oldest interpretation of quantum mechanics relies on a collapse. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, is the traditional and most widely taught view of quantum mechanics. It posits that a quantum system exists in a superposition of all its possible states, described by a mathematical tool called a wave function. This wave of possibility evolves smoothly over time until a measurement is made. At the moment of measurement, the wave function undergoes a sudden, random, and irreversible collapse, forcing the particle to choose one definite state. In this view, reality is fundamentally probabilistic, and the observer plays a crucial, if mysterious, role in turning potential into actuality. Fact 41. An alternative theory says particles are always real. Not all physicists were comfortable with the randomness and observer dependence of the Copenhagen interpretation. An alternative, known as pilot wave theory or de Broglie-Bohm theory, offers a different picture. It suggests that particles like electrons are always real, definite particles, with a definite position at all times, even when we are not looking. However, their movement is guided by a real, physical pilot wave. The particle is like a tiny surfer, and the wave function is the ocean wave that tells it where to go. This theory perfectly reproduces all the predictions of standard quantum mechanics, but it does so without randomness or the collapse of the wave function, suggesting a hidden, deterministic layer beneath the quantum world's apparent chaos. Fact 42. Ghostly particles are streaming through you right now. Trillions of tiny, elusive particles called neutrinos are passing through your body every single second. Produced in the nuclear reactions of the Sun and other cosmic events, Neutrinos are one of the most abundant particles in the universe. They have an almost imperceptibly small mass and no electric charge, which means they barely interact with other matter at all. A neutrino could travel through a light year of solid lead with only a 50% chance of being stopped. They are the ultimate cosmic ghosts, silent messengers that carry information directly from the heart of stars, offering us a clear window into the universe's most violent and hidden processes. Fact 43. Neutrinos are cosmic shapeshifters. There are three different types, or flavors, of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. The strange thing is, they don't stick to one identity. As a neutrino travels through space at nearly the speed of light, it can spontaneously and periodically change from one flavor to another in a process called neutrino oscillation. This shape-shifting ability was a major discovery, as it proved that neutrinos must have mass, however small. It solved a long-standing mystery of why early experiments detected fewer solar neutrinos than predicted. They were simply changing their flavor on the journey to Earth. Fact 44. Reality has a kind of charge that is not electrical. In addition to electric charge, quarks possess a different kind of charge related to the strong nuclear force. This charge is called color charge. It has nothing to do with visible colors, but it behaves in a similar way. There are three types of color charge: red, green, and blue, as well as their anticolors. The rule is that quarks can only exist in combinations that are color neutral. A proton, for example, contains one red, one green, and one blue quark, which combine to make white, or neutral. This quirky and beautiful system, described by the theory of quantum chromodynamics, is the reason the strong force can bind quarks so powerfully while having almost no effect on the world outside the atom's nucleus. Fact 45. The theory of light and electrons is our most perfect theory. Quantum electrodynamics, or QED, is the quantum field theory of electromagnetism. It describes how light, photons, and matter, electrons, interact. It is arguably the most successful and precisely tested theory in the history of science. Its predictions, such as the magnetic moment of the electron, have been experimentally verified to an astonishing degree of accuracy, equivalent to measuring the distance from New York to Los Angeles to within the width of a single human hair. QED, with its elegant Feynman diagrams, became the template for building the other parts of the Standard Model, and it remains a monumental achievement of human intellect. Fact 46. A single number holds the key to our universe. There is a fundamental constant of nature known as the fine structure constant, represented by the Greek letter alpha. Alpha. It is a pure number, approximately equal to 1137. It governs the strength of the electromagnetic force, dictating how strongly charged particles like electrons interact with photons. If this number were just a few percent different, the universe would be unrecognizable. Stars would not be able to form stable carbon atoms, and life as we know it would be impossible. Why this number has the precise value it does is one of the deepest mysteries in physics. It appears to be a perfectly tuned cosmic dial, a silent, dimensionless number that makes our existence possible. Fact 47. An excited atom can decay all by itself. An atom in a high energy, or excited, state will eventually drop to a lower energy state by emitting a photon. This can be triggered by an outside influence, but it can also happen completely on its own, a process called spontaneous emission. This is a purely quantum phenomenon, a result of the atom's interaction with the zero-point energy of the vacuum. The quantum foam of virtual particles in empty space can gently nudge the excited electron, causing it to make the quantum leap to a lower state and release its energy as a real photon. It is a beautiful example of how the ever-present quantum vacuum can have a real and observable effect on the world of matter. Fact 48. Entanglement cannot be used for instant communication. The spooky, instantaneous connection between entangled particles seems like it could be a perfect tool for faster-than-light communication. However, the laws of the universe have a clever safeguard in place. While measuring one particle instantly affects its partner, the outcome of your measurement is always completely random. You cannot force your particle to be heads to send a 1 or tails to send a 0. You can only know after the fact that your friend's particle must be the opposite. To make sense of the correlation, you still have to call your friend on a regular, light-speed limited phone to compare notes. The spooky action is a private, silent understanding between the particles, not a public broadcast system. Fact 49. The largest structures in the universe were born from quantum jitters. The vast cosmic web of galaxies and galaxy clusters we see today has its origins in the very first moments of the universe. In the instant after the Big Bang, the universe was an incredibly tiny, dense, quantum object. Tiny, random quantum fluctuations, the same kind that create the quantum foam, caused minuscule variations in the density of this primordial soup. Then, a period of incredible expansion called cosmic inflation stretched the universe exponentially, blowing these tiny quantum fluctuations up to astronomical sizes. These slightly denser regions became the gravitational seeds around which all the stars and galaxies we see today would eventually form. The grandest structures in the cosmos are direct echo of the quiet, random whispers of the quantum world. Fact 50. The universe plays dice. At its core, quantum mechanics is a theory of probabilities. Unlike classical physics, which is deterministic and allows you to predict the exact future of a system if you know its present state, quantum mechanics only allows you to calculate the probability of different outcomes. The wave function of a particle tells you the odds of finding it here or there, but it can never tell you with certainty where it will be. Albert Einstein famously disliked this randomness, stating, "God does not play dice with the universe." But a century of experiments has overwhelmingly shown that, at the most fundamental level, the universe does indeed seem to rely on chance. Reality is not a predetermined clockwork, but a gentle, unfolding game of probability. Fact 51. Lasers are a direct product of quantum mechanics. A laser beam, with its perfectly straight, pure-colored, and intensely focused light, is a beautiful demonstration of quantum principles in action. The word laser is an acronym that stands for light amplification by stimulated emission of radiation. The process works by exciting a large number of atoms in a material to the same high-energy quantum state. A single photon is then used to trigger one of these atoms to drop to a lower state, releasing a second photon that is a perfect clone of the first. Same color, same direction, same phase. This new photon then stimulates other atoms, creating a chain reaction that results in a cascade of identical, perfectly coherent photons, a powerful, unified river of light born from a single quantum whisper. Fact 52. Atoms can be stimulated to release their light. An excited atom left alone will eventually emit a photon spontaneously, in a random direction. But in 1917, Albert Einstein realized that this process could be controlled. If a photon with the correct energy passes by an atom that is already in an excited state, it can stimulate that atom to release its stored energy as a second, identical photon. This process, called stimulated emission, is the key to the laser. It allows us to build a cascade of perfectly ordered light, proving that even the random quantum leaps of an atom can be gently coaxed into a state of perfect, harmonious cooperation. Fact 53. Quantum mechanics has never once been wrong. In its nearly century-long history, quantum theory has been subjected to the most rigorous and extensive experimental testing of any theory in science. And in all of those tests, it has never failed. Its predictions have been confirmed time and time again with astonishing accuracy. While it remains deeply counterintuitive and philosophically puzzling, its mathematical framework has proven to be a flawless description of the subatomic world. It is the most successful physical theory ever devised by humanity, a quiet and unwavering testament to the strange and beautiful rules that govern the very foundation of reality. Fact 54. A particle can feel a force it never touches. In a strange phenomenon called the Oharonov-Bohm effect, a charged particle like an electron can be influenced by a magnetic field that exists in a region it never physically enters. Imagine an electron traveling in a loop around a shielded magnetic field. Even though the electron only travels through areas where the magnetic field is zero, its wave function can still feel the field's potential on the other side of the barrier. This subtle influence shifts the phase of the electron's wave, an effect that can be measured. It proves that the quantum world is non-local. The state of a particle is determined not just by its immediate surroundings, but by the entire landscape of fields and potentials around it. Fact 55. The heart of an atom is a quantum dance. The nucleus of an atom, a tiny, dense core of protons and neutrons, is itself a complex quantum system. The particles within it are not static little balls but are in a constant state of motion, governed by the probabilistic rules of quantum mechanics. They exist in quantized energy shells, similar to the shells of electrons orbiting the nucleus, but far more complex. The stability of a nucleus, and whether it is radioactive, depends on the delicate balance of the powerful strong force holding it together and the electromagnetic force trying to push its protons apart. It is a quiet, intricate dance of forces and probabilities at the heart of all matter. Fact 56. Quantum mechanics creates a tiny bit of friction in a vacuum. According to some theories, there should exist a force called quantum friction. If you were to move a neutral, uncharged atom through a perfect vacuum close to a surface, it would experience a tiny, almost imperceptible drag force. This force doesn't come from air resistance, but from the atom's interaction with the quantum foam. As the atom moves, it disturbs the virtual particles of the vacuum, creating fluctuations that gently pull back on it, slowing it down. While incredibly difficult to measure, this effect demonstrates that even the most perfect emptiness of space has a subtle substance to it, a quantum texture that resists motion. Fact 57. The Lamb shift revealed the true complexity of the vacuum. Early quantum theory predicted that two specific energy levels in a hydrogen atom should have exactly the same energy. In 1947, Willis Lamb performed an experiment that showed there was actually a tiny, unexpected difference between them. This is now called the Lamb shift. The explanation came from the full theory of quantum electrodynamics, which showed that the electron in the atom is constantly interacting with the virtual particles of the quantum foam. This subtle interaction with the vacuum itself slightly shifts the electron's energy, accounting for the tiny difference. It was a major triumph for QED, proving that the emptiness of space plays an active and measurable role in shaping the structure of atoms. Fact 58. Black holes are not entirely black. Stephen Hawking famously combined quantum mechanics with the theory of gravity to show that black holes should slowly evaporate over time. This happens because of virtual particle pairs popping into existence at the very edge of the black hole's event horizon. Occasionally, one particle of a pair will fall into the black hole while the other escapes into space. To an outside observer, it appears as though the black hole itself has emitted a particle. This slow leak of particles, known as Hawking radiation, causes the black hole to lose mass over an unimaginably long period, a quiet, steady glow from the darkest objects in the universe. Fact 59. A particle can take every possible path at once. Richard Feynman developed a powerful and intuitive way of looking at quantum mechanics called a path integral formulation. It states that to get from point A to point B, a particle does not take a single, specific path. Instead, it simultaneously explores every single possible path it could take. Straight lines, curved lines, wild zigzags across the universe and back again. The probability of finding the particle at point B is then calculated by summing up the contributions of all these infinite paths. It is a breathtaking picture of the quantum world, where a single particle is an infinite explorer, its final destination determined by a democratic vote of all the journeys it could have possibly made. Fact 60. The building blocks of life use quantum magic. The enzymes in our bodies, which are the catalysts for almost every biological reaction, work with an efficiency that classical chemistry struggles to explain. It's now believed that they use quantum tunneling to speed things up. To make a reaction happen, molecules need to overcome an energy barrier. Enzymes help by lowering this barrier, but they also allow particles like protons to simply tunnel through the remaining barrier instead of having to climb over it. This quantum shortcut can speed up reactions by a factor of thousands or even millions, making life as we know it possible. It is a quiet, efficient magic happening in every one of your cells. Fact 61. Quantum states can be measured without being disturbed. A key principle of quantum mechanics is that measurement disturbs a system, but a technique called interaction-free measurement allows us to see an object without a single photon ever touching it. It works by placing an object in one of the possible paths of a single photon in an interferometer. If the object is present, its very potential to absorb the photon collapses the photon's wave function in a specific way that can be detected at the output, even though the photon never actually hit the object. It is a gentle, ghostly way of knowing something is there, purely by acknowledging the possibility that it could have been seen. Fact 62. Albert Einstein was quantum theory's greatest critic. Although his own work was foundational to quantum mechanics, Einstein was deeply troubled by its implications, particularly entanglement and randomness. To challenge the theory, he and his colleagues devised a thought experiment called the EPR paradox. They argued that the spooky connection between entangled particles must mean the theory was incomplete, and that the particles must have hidden local properties, hidden variables, that determine their state from the moment they are created. It was an attempt to restore a classical, deterministic, and local reality to the quantum world. Fact 63. An Irish physicist proved Einstein wrong. For decades, the debate over hidden variables remained a philosophical one. Then, in the 1960s, a physicist named John Stuart Bell devised a brilliant mathematical theorem. Bell's theorem proved that if hidden variables were real, then the correlations between measurements on entangled particles would have to be below a certain limit. But if quantum mechanics was correct, those correlations would be stronger. When the experiment was finally performed with enough precision, the results were clear. The correlations were stronger, exactly as quantum mechanics predicted. It was a profound discovery, proving that the universe is fundamentally non-local and that Einstein's spooky action at a distance is a real and undeniable feature of our reality. Fact 64. Space and time may be made of tiny loops. String theory is not the only candidate for a theory of quantum gravity. A competing theory is called loop quantum gravity. This theory takes a different approach. Instead of starting with particles, it starts with space-time itself. It proposes that the fabric of spacetime is not smooth and continuous, but is woven from a network of finite, quantized loops, like tiny threads in a cosmic cloth. These loops are the fundamental atoms of space and volume. In this view, spacetime is not the stage on which quantum events happen. Spacetime itself is a quantum mechanical system, a shimmering, discrete network that gives rise to the reality we perceive. Fact 65. The universe has a cosmic speed limit for cause and effect. The theory of special relativity is a crucial part of quantum field theory, and it sets a universal speed limit, the speed of light in a vacuum. Nothing, no object, no information, no causal influence, can travel faster than this speed. This principle of locality is essential for a consistent universe. While entanglement seems to violate it, the no communication theorem ensures that no useful information can be sent faster than light. This cosmic speed limit ensures that cause always precedes effect, preserving the logical, ordered structure of our universe, even with all its quantum strangeness. Fact 66. Quantum mechanics protects us from atomic collapse. A classical atom, as imagined in the 19th century, with an electron orbiting a nucleus like a planet orbiting the Sun, is completely unstable. According to classical physics, an orbiting charged particle should constantly radiate away energy, causing the electron to spiral into the nucleus in a fraction of a second. All atoms should instantly collapse. The reason they don't is quantum mechanics. The rule that electrons can only exist in specific, quantized energy levels, or orbitals, prevents them from radiating continuously. They are locked into stable orbits, a quiet, quantum law that guarantees the very existence of matter. Fact 67. The father of the uncertainty principle had a gentler view. Werner Heisenberg is famous for his uncertainty principle, which places a hard limit on what we can know. But his own philosophical view of quantum mechanics was deeply nuanced. He saw the wave function not as a physical wave, but as a statement of knowledge. It represented what we knew about a system. The act of measurement was not a violent collapse, but a simple updating of our knowledge. He saw the quantum world as a world of potentiality, a realm of possibilities that is gently transformed into the actuality of our classical world through the act of observation and learning. Fact 68. The vacuum of our universe may be unstable. Some theories in physics suggest that our universe exists in a false vacuum. This means that while our vacuum seems stable, it is not in the lowest possible energy state. It's like a ball resting in a small dip on the side of a great mountain. A sufficiently large jolt, perhaps from a random quantum fluctuation, could tip it over the edge, causing it to roll down to the true, lower energy vacuum. If this were to happen, a bubble of this new vacuum would expand at the speed of light, rewriting the laws of physics and dissolving every structure within it. It is a quiet, distant possibility that the ground state of our reality is only temporary. Fact 69. Classical reality is selected by the universe. Why do we all agree on the location of a tree or a stone, when its quantum components are a blur of possibilities? The theory of quantum Darwinism offers an answer. It suggests that a quantum system's information, like a particle's position, is copied over and over again into its surrounding environment. Only certain states, the most stable and robust ones, can create many copies of themselves without being destroyed. The environment acts as a massive witness, and our shared, classical reality is simply the information that has been redundantly and reliably recorded for everyone to see. It is a process of natural selection for facts. Fact 70. A particle can spin 360 degrees and not return to its starting point. In our world, a full rotation brings an object back to where it began. But for a fundamental particle with half-integer spin, like an electron, this is not true. Its wave function is described in such a way that it must rotate a full 720 degrees, 2 complete turns, to return to its original quantum state. You can visualize this with a simple trick. Place your hand flat, palm up. Rotate it 360 degrees by turning it under your arm. Your hand is oriented correctly, but your arm is twisted. You must perform another full 360-degree rotation in the same direction to return your arm to its original, untwisted state. The electron spin behaves in a similarly strange and beautiful way. Fact 71. There are particles that only exist in 2 dimensions. In our 3-dimensional world, all particles are either bosons or fermions. But if you confine electrons to a thin, 2-dimensional plane, exotic particles called anyons can emerge. These quasi-particles have strange quantum properties unlike any other. When you swap the position of 2 identical fermions, their wave function gets a negative sign. When you swap 2 bosons, nothing changes. But when you swap 2 anyons, their wave function can change by any phase, hence the name enyon. They are a quiet testament to how the laws of physics can change in different dimensional landscapes. Fact 72. We can build artificial atoms. Scientists can create tiny crystals of semiconductor material, only a few nanometers across, called quantum dots. These dots are so small that the electrons trapped inside them begin to behave just like electrons in a single, giant atom. Their energy levels become quantized, and they can absorb and emit light of very specific colors. By simply changing the size of the quantum, scientists can precisely tune the color of light it emits. These artificial atoms are now used in everything from vibrant television displays to fluorescent markers in biological research, a beautiful fusion of quantum physics and nanotechnology. Fact 73. You can know a bomb is working without ever touching it. The Elitzer-Vaidman bomb testing problem is another fascinating interaction-free measurement thought experiment. Imagine you have a set of bombs, some of which are duds and some of which have a supersensitive trigger that will cause them to explode if a single photon touches it. Using a clever quantum interferometer, you can send a single photon on a path where it has the potential to interact with the bomb's trigger. In some cases, you can determine with certainty that the bomb's trigger is functional, and therefore the bomb is live, without the photon ever having to take the path that would have set it off. It is a gentle, careful way of probing reality without disturbing it. Fact 74. Quantum logic is not our logic. In our everyday classical world, a statement is either true or false. A cat is either in the room or it is not. But in the quantum world, this binary logic breaks down. A quantum proposition can be true, false, or in a state of superposition, a blend of both true and false. This has led to the development of quantum logic, a different way of reasoning that can handle the inherent indeterminacy of the quantum world. It is a formal system that reflects a reality where a particle can be in a superposition of here and not here until a measurement forces a classical, binary answer. Fact 75. There are crystals that repeat in time, not just space. A normal crystal is a solid whose atoms are arranged in a repeating pattern in space. In 2012, Nobel laureate Frank Wilczek theorized about a new state of matter, a time crystal. This is a quantum system that repeats its structure not in space, but in time. Even in its lowest energy ground state, a time crystal has components that are in perpetual, periodic motion, breaking time translation symmetry. It's like a clock that ticks forever without any energy input. For years they were purely theoretical, but scientists have now successfully created real time crystals in the lab, revealing a strange and beautiful new phase of matter that is eternally restless. Fact 76. All forces are just an exchange of messages. According to quantum field theory, the fundamental forces of nature are not some mysterious, invisible pulling or pushing. They are the result of particles constantly exchanging other particles. The electromagnetic force, for example, is mediated by the exchange of virtual photons. When 2 electrons repel each other, they are essentially playing a gentle game of catch, tossing virtual photons back and forth. The strong force is the exchange of gluons, and the weak force, the exchange of W and Z bosons. Every interaction in the universe, from the gentlest touch to the most violent explosion, is a silent, continuous conversation carried by these fundamental messenger particles. Fact 77. The universe might be computing its own future. The universe is filled with quantum particles interacting, creating, and destroying information. This has led some physicists to a profound idea that the universe itself is a kind of quantum computer. In this view, the laws of physics are the algorithm, and the evolution of the cosmos from the Big Bang onwards is the computation it is performing. Every quantum interaction is a tiny step in this grand calculation, processing information and determining the next state of the universe. It is a beautiful metaphor that recasts reality not as a collection of objects, but as a single, vast, and ongoing information process. Fact 78. The ultimate secret message would be a quantum one. The principles of quantum mechanics can be used to create a perfectly secure communication system. This is the field of quantum cryptography. One method works by sending information encoded in the quantum states of individual photons. According to the observer effect, if an eavesdropper tries to intercept and measure these photons to read the message, their very act of measurement will inevitably disturb the photon states. The intended recipients can then perform a test on a sample of the photons, and if they detect any disturbance, they will know instantly that their communication line has been compromised. It is a secret code that is protected by the fundamental laws of physics itself. Fact 79. Quantum mechanics is a theory of relationships. We tend to think of particles as having intrinsic properties. This electron has a specific position, that photon has a specific polarization. But a more relational interpretation of quantum mechanics suggests that a particle's properties have no meaning in isolation. They are only defined in relation to the measurement device or the other systems they interact with. An electron has no definite position until it interacts with a detector that asks the question, "Where are you?" Reality, in this view, is not a collection of independent things, but a vast, interconnected network of interactions and relationships. Nothing truly exists on its own. Fact 80. Quantum effects are happening in your brain. The human brain is a warm, wet, and complex environment, which makes it difficult for delicate quantum states to survive. However, some researchers have proposed that certain quantum phenomena may play a role in consciousness. One controversial theory, the Ochoa theory, suggests that quantum computations could be happening inside tiny protein structures within our neurons called microtubules. While there is no definitive proof, it is a tantalizing idea that the deepest mystery of science, the nature of consciousness, might be linked to the strange and wonderful rules of the quantum world, a quiet internal dance of quantum coherence. Fact 81. The universe may be a hologram. The holographic principle is a startling idea that emerged from the study of black holes. It suggests that all the information contained within a three-dimensional volume of space, like our universe, can be completely described by the physics on its two-dimensional boundary or surface. This is like a hologram, where a 2D surface contains all the information needed to project a 3D image. This principle suggests that the three-dimensional world we experience might be an illusion, a projection of information stored on a distant cosmic horizon. It is a profound rethinking of the nature of space and information itself. Fact 82. Your body is mostly empty space held together by quantum rules. The atoms that make up your body are over 99.99999% empty space. The feeling of solidity you experience is an illusion created by quantum mechanics. The reason your hand doesn't pass through a table is not because their atoms are physically bumping into each other, but because of the Pauli exclusion principle and the electromagnetic repulsion between the electron clouds of their atoms. This powerful but gentle quantum resistance is what gives matter its familiar solidity and form, weaving a world of tangible substance from an ocean of cosmic emptiness. Fact 83. There is no single story of the universe. In the classical world, we imagine there is a single, definite history of the universe. But Richard Feynman's path integral formulation suggests a different view. Just as a particle takes all paths, the universe itself, in its earliest quantum state, may have explored all possible histories. The single, classical history we observe is simply the one that emerged from the sum of all these possibilities. This is the idea of sum over histories. It suggests that the past is not a single, fixed timeline, but a superposition of every possible story that could have led to our present moment. Fact 84. A particle has no identity until it interacts. In the quantum world, identical particles like electrons are truly, perfectly indistinguishable. You cannot paint one red and one blue to keep track of them. Quantum mechanics tells us that before an interaction, it is meaningless to even ask which electron is which. They exist in a state of shared identity. This profound lack of individuality is a core feature of the quantum world, and it gives rise to many strange phenomena, including the Pauli exclusion principle and the unique behaviors of bosons and fermions. Fact 85. Quantum physics reveals a deeply connected world. Perhaps the most profound insight from quantum mechanics is that the universe is not a collection of separate, isolated objects. It is a single, indivisible whole. The principle of entanglement shows that two particles can be linked in a way that transcends space and time. The non-locality of the Oharonov-Bohm effect shows that a particle's behavior is influenced by the entire field around it. And quantum field theory shows that all particles are just ripples in the same underlying cosmic fields. It is a quiet, scientific echo of an ancient spiritual wisdom, that all things are deeply and fundamentally interconnected. Fact 86. The wave function of the universe is a gentle, guiding equation. If a single particle can be described by a wave function, can the entire universe? Many physicists believe so. The Wheeler-DeWitt equation is a theoretical attempt to write down the wave function for the entire cosmos. It is a strange and timeless equation that does not contain the variable t for time, suggesting that at the most fundamental level, the universe may be static. In this view, the passage of time we experience is an emergent property of the relationships between the parts of the universe, not a fundamental feature of reality itself. It is a quiet, mathematical glimpse of a universe seen from outside of time. Fact 87. We are all quantum beings. Every atom in your body, every electron firing in your neurons, every photon of light entering your eyes, is governed by the strange and beautiful laws of quantum mechanics. The stability of the ground you stand on, the warmth of the sun, and the very chemistry of life are all manifestations of this hidden reality. You are not just an observer of the quantum world. You are a part of it. You are a vast, coherent collection of quantum systems, a walking, thinking, feeling wave function, a quiet, temporary eddy in the great quantum fields of the cosmos. Fact 88. Quantum mechanics is not a single theory, but a set of rules. It is a fundamental framework, a new kind of grammar for the universe. Theories like quantum electrodynamics or the Standard Model are built using this grammar, but the rules themselves are more profound. They tell us about the existence of quanta, wave-particle duality, superposition, and uncertainty. It is the underlying operating system of reality, and all the specific theories of particles and forces are like applications that must run on this strange and beautiful system. Fact 89. There is a single number that defines the quantum world. The Planck constant, represented by the letter h, is one of the most important numbers in all of physics. It is an incredibly tiny number that acts as the fundamental measure of the quantum realm. It is the number that determines the size of energy quanta, the scale of the uncertainty principle, and the wavelength of a particle. If the Planck constant were zero, the universe would be entirely classical. Its small but non-zero value is the single reason the universe has a shimmering, probabilistic, and gentle layer of reality hidden beneath our own. Fact 90. All electrons are perfect, identical clones. In our world, no two objects are ever perfectly identical. 2 grains of sand will always have some subtle difference. But in the quantum world, this is not true. Every single electron in the universe is a perfect, flawless copy of every other electron. They have the exact same mass, the exact same charge, the exact same spin. There are no distinguishing marks or features. This perfect identity is a fundamental property of nature, and it is essential for the laws of chemistry and the stability of matter. It is a quiet testament to the profound order and consistency that underlies the quantum world's apparent chaos. Fact 91. The vacuum is in the eye of the beholder. The Unruh effect is a startling prediction of quantum field theory. It states that an observer who is accelerating will perceive a warm bath of thermal radiation around them, while an observer who is stationary in the same location would perceive only a cold, empty vacuum. This means that the very concept of empty space, and even the number of particles in a region, is relative to the observer's state of motion. The reality you experience is tied to how you move through it. It's a gentle reminder that there is no single, absolute reality, but a tapestry of different perspectives. Fact 92. The line between order and chaos is blurry. Quantum chaos is a field of study that explores how the chaotic behavior of classical systems, like the weather or the orbits of planets, emerges from the orderly, wave-like nature of quantum mechanics. It is a deep and difficult puzzle. In the quantum world, waves are smooth and predictable, but in our world, things can be messy and chaotic. Understanding this transition helps us see how the familiar, unpredictable world we know can be born from the strange but deterministic evolution of the quantum wave function. It is the search for the quiet mathematical bridge between the two realms. Fact 93. Quantum mechanics is a story with many possible endings. While all the different interpretations of quantum mechanics, like Copenhagen, many worlds, and pilot wave theory, give the exact same predictions for experiments, they tell wildly different stories about the nature of reality. Is reality random or deterministic? Does the observer create the outcome, or does the universe split into infinite copies? Is there a hidden layer we cannot see? Science cannot yet tell us which story is true. It remains a profound philosophical choice, a gentle invitation to wonder about the ultimate nature of what is real. Fact 94. The quantum world challenges our very idea of a thing. We are used to a world of objects with definite properties. A ball is red, it is here, it is solid. But quantum mechanics tells us that, at a fundamental level, this is not how reality works. A particle does not have a definite position or a definite momentum until it is measured. Before that, it is only a wave of potential. This forces us to reconsider our deepest intuitions. It suggests that the universe is not made of things, but of processes, relationships, and possibilities, a dynamic and ethereal dance rather than a static collection of objects. Fact 95. We live in a universe of waves. The deepest lesson of quantum field theory is that the world is not made of tiny billiard balls. The fundamental reality is a set of vast, invisible, and interconnected fields. What we perceive as particles are just the smallest possible ripples in these fields. The solidity of matter, the energy of light, the pull of a force, all are manifestations of the behavior of these underlying waves. It is a quiet, profound shift in perspective, suggesting that we live not in a world of matter, but in an ocean of ethereal, vibrating fields. Fact 96. Our brains were built for a different world. The reason the quantum realm feels so strange and counterintuitive is that our minds evolved to understand the classical world, the world of thrown spears and ripening fruit. Our intuition for physics is based on our experience with large, slow-moving objects. We have no everyday experience with superposition or entanglement, so our brains have not developed an innate ability to grasp them. To understand the quantum world, we must rely on the quiet, abstract language of mathematics and be willing to let go of our most deeply held common-sense assumptions. Fact 97. Information is a physical thing. In the 21st century, the study of quantum mechanics is increasingly merging with the study of information. Physicists now understand that quantum information is a fundamental new resource. The state of a qubit is not just a description of a particle. It is a unit of information that can be processed and transmitted. This realization is what drives the quest for quantum computing and quantum communication. It reframes the universe not just as a collection of matter and energy, but as a vast processor of quantum information, a quiet, cosmic computer running on the laws of physics. Fact 98. Quantum effects are tiny, but their consequences are everything. The Planck constant, which governs the quantum world, is an incredibly small number. This is why we don't see quantum weirdness in our daily lives. But the cumulative effect of these tiny rules is what makes our universe possible. Without the Pauli exclusion principle, matter would collapse. Without quantized energy levels, atoms would not be stable. Without quantum tunneling, the sun would not shine. The grand, classical world we see is built upon and completely dependent on this quiet, invisible, and shimmering foundation. Fact 99. The ultimate dream of physics is a quantum one. For a century, physics has been defined by two great pillars: Einstein's general relativity, which describes the grand scale of gravity and the cosmos, and quantum mechanics, which describes the small scale of particles and forces. These two theories are incredibly successful in their own domains, but they are fundamentally incompatible. The greatest challenge in modern physics is to unite them into a single, deeper theory of quantum gravity, a theory of everything. This quest, whether it leads to string theory or loop quantum gravity or something entirely new, is the ultimate attempt to find a single, quiet equation that can describe the entire universe in one elegant thought. Fact 100. The deepest truth is a quiet wonder. We have journeyed through the strange and beautiful landscape of the quantum world, from the smallest pixel of space to the birth of the cosmos. We have seen particles that are also waves, that exist in many places at once, and that are connected by an invisible thread. Yet for all we have learned, the greatest truth of quantum mechanics is that it leaves us in a state of profound and gentle wonder. It reminds us that the universe is more clever, more subtle, and far more mysterious than we could ever have imagined. And the quiet invitation to simply be in awe of that mystery is the most beautiful fact of all.